Hey, it's Mrs. Marat here with just a little bit of help um, to get you ready for your Algebra 2 final. So I'm not going to go through all of the problems in the packet. I am going to focus on just kind of a selection of problems from each of the units or each of the parts of the units that we covered in this semester. And so let's get started here. Unit 1, which is on sequences and functions. And so we had to determine in Unit 1, first of all, whether a sequence was arithmetic or geometric. So an arithmetic sequence has a common rate of change. And so that means you're like adding the same value in each step of the sequence. Whereas a geometric sequence, you have a common ratio. So you're multiplying by the same number over and over to generate the terms in the sequence. So when I'm actually going to do problem 1, but I just wanted to show you on a graph, arithmetic sequences line up like this. So this is an example of arithmetic. And geometric sequences, they make like that exponential looking curve. And so this would be an example of a geometric sequence. Okay, so you can practice those two on your own. I'm just going to do the first one here for some help. So the first thing is to determine, is it arithmetic, meaning it adds the same number from step to step, or is it geometric, meaning it multiplies by the same number from step to step? So the first thing that I'm going to do to figure that out is figure out, well, is this adding or multiplying? So if it were adding, 7 plus 9 is equal to 16. So I'm just going to check it the rest of the way. If I add 9 to 16, yep, we get 25. And 25 plus 9 is 34. And 34 plus 9 is 43. And so this is definitely an arithmetic sequence. Circle arithmetic. And then we have two different like equations or formulas to write function rules, I should say, for this. One in what's called recursive form, and the other one, it's called explicit form, or writing a definition for the nth term. So recursive form has two parts. It tells us where to start. So this starts when n is 0, and the value is 7. So we use function notation and say, first of all, a of 0, and I'm using a because this is sequence A. So a of 0 is equal to 7. And then the next part of a recursive formula tells us, like, what do you do to each term to get the next term? And so I take this term, I add 9. I get this term, I add 9. So that's the second part. So the way that we write that in function notation is we use a of n. So for any term in general, it's equal to a of n minus 1, which means the term before it, right? So if this is the 5th term, this means the 4th term. And so you take that term and you add 9 to it. So plus 9. Okay, so recursive definitions always have these two parts. And then write a definition for the nth term. So the nth term just kind of puts these two things together. So I know it starts at 7 and it adds 9 for every new n value. Okay, and so what I usually do when I write an explicit, because sometimes you have to put an n minus 1 here. And so what I usually do when I am writing this as an explicit is I just like take a combination from the table and then have to just check, does my rule make that combination happen? So with what I just said to do, if I start here, 7 plus 9, if n is 4 times 4, see how we got 43? So that tells me I made my rule correctly because it worked. Yay. So that's all I'm going to go over for, oh, just kidding, there's 2 more parts. So A of 5 and then A of 30. So we just, now that you have a rule made, you are going to replace the n in your rule with 5 and find the answer. So 7 plus 9 times 5. And then do the same thing for the 30. Okay. So I could just add 9 because the 5th term is going to be the one right after the one we know. So I could just add 9 to that or just type it in. 7 plus 9 times 5 is 52. And 7 plus 9 times 30 is 277. So 52 and 277. Excuse me. All right. And so I'm going to pause and get some water. Maybe. Looks like my pausing option is not working. So it's okay. All right, so the next unit we did was polynomials, and the polynomial problems that I want to go over, just 2 of them from the polynomial section on the review. Number 6b. So if you're actually in my class, we did go over number 6a already. So I'm going to go over number 6b for just one more look at the idea. All right, so we have to write this as a product of linear factors. That's our goal. So we know one of the linear factors is 3x plus 1. So I'm going to put that here. It's the first part of the answer. And we have to find 2 more parts. And I know it's 3 parts altogether because of the exponent here of 3. All right. So I'm going to divide out using the, I'm like choking and my eyes are watering. I'm sorry, but the things I do so you can do well in math. So we're going to divide out the 3x plus 1 from this big polynomial. So I'm going to use the box. And then remember, to start this, we take that very first term in the polynomial, this one, and we put it right here. That's how we start. And so 3x to the third goes here. And then that allows us to know what goes on the top. It's x squared, because x squared times 3x is how you get the 3x to the third. And then you just multiply it by the 1. So x squared times 1 is x squared. And we go to the next spot. Okay, so it's really tempting to put negative 5x squared in the next spot because that's our next target. But we already have x squared. So this box and this box have to total negative 5x squared. Okay, so this is 1x squared. We have to take away 6x squared to total negative 5x squared. And so that means negative 2x goes up here. Negative 2x times 3x is negative 6x squared. And then negative 2x times 1 is negative 2x. All right, we're cruising now. Our next target is negative 26x squared. And that's going to be the total of this box and this box. Okay, so to get all the way to negative 26, and we're at negative 2, we need to add negative 24x, which means negative 8 goes up here because negative 8 times 3x is negative 24x. And then negative 8 times 1 is negative 8. And now we know that we've actually done this correctly because this was our final target, and that's what we ended with in the box. So it divided in evenly. And so now we take what was at the top, x squared minus 2x minus 8, and then factor it. So that multiplies to negative 8 and adds to negative 2. It's negative 4 and positive 2. And so these two values finish up our linear factor. Sorry, x minus 4 and x plus 2. Okay, so this is a minus 4 right there. All right. So that was rewriting in factored form. And then we also did this graphing one in class, but in case you missed something, I just want to go over it really quick, especially finding the intercepts and the end behavior. Okay, so our x-intercepts come from the values of x in the factored form that would make the factor equal to 0. So for x plus 3, a negative 3 would make that equal to 0. And because this one's being squared, I'm going to write it down twice to remind myself that it makes a bounce on the graph. For x plus 1, a factor of negative, or a value of negative 1 would make it equal 0. So that's going to give us an x-intercept of negative 1. And then for 3x plus 4, the x-intercept is 4/3. And you can get that by solving this equation. Add the 4, you get 3x equals 4. Divide by 3, you get x equals 4/3. Okay, so all of our intercepts come from, x-intercepts come from making the factor equal to 0 and then solving for x. Okay? All right, so those are the x-intercepts. So negative 3 is here, negative 1 is here. 4/3 is just like a little more than 1. So I'm going to put a little tiny b next to this one to remind me it's going to bounce right there. Okay. Next is the y-intercept. The y-intercept, you know, where does this function, where does this function cross the y-axis? Every point on the y-axis has an x value of 0. And so to find the y-intercept, we put a 0 in the equation every place that you see an x. So it's 2 times 3 times 0 minus 4 times 0 plus 1 times 0 plus 3 squared. And if you want to shorten this up, you certainly could, because the next, like this is 0. 0 minus 4 is negative 4. 0 plus 1 is 1, and 0 plus 3 is 3, and that is being squared. So you could definitely shorten that up if you didn't want to put all of this into the calculator. Anyways, when you do, you get negative 72. And so that means somewhere down here is where the function's going to cross the y-axis. Then the last thing to do before, I do the graph and then I state the end behavior, because to me that makes more sense, because I really understand how to graph. That way I don't have to memorize a whole bunch of rules. All I have to know is that this is how I know, this is a positive 2 leading in the function. So it's all positive. It's going to be a positive function overall, which means that the function ends in the positive direction. So if I know it ends in the positive direction, that's the last x-intercept. So it goes up from there and then down through the y-intercept, back up to here, turns around, bounces at negative 3, and then that's the last x-intercept on that side. And so this is what the graph looks like. And for the end behavior, the first statement says as x gets smaller in the negative direction, so starting at 0, that way, it's asking me to state is that arrow headed into the positive or negative direction? So g of x gets larger in the positive direction because the arrow is headed up. And then on the other side, as x gets larger in the positive direction, that's this way, g of x, the function, it's also getting larger in the positive direction. Okay, so I'm going to put a plus right here for positive. All right, so that's what I wanted to cover about graphing polynomial functions. Next, we're just going to talk for a moment about asymptotes. Okay, so let's look at rational functions and then asymptotes. So we've got this one rational function right here, and we've got some graphs here, okay? So it says the graph of two rational functions are shown. One of them is this expression, 5x minus 3 divided by x. Which graph is it? Explain how you know. And so before getting to that, I just want to talk about, well, what are the asymptotes of this graph? So I can clearly see this graph has a horizontal asymptote. It's going this way through 5 on the y-axis. So this is y equals 5. And then this one is just the x equals 0. Okay, so those are the asymptotes for that function. This one also has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals negative 5. So it appears that they have everything in the x asymptotes in common, the vertical, but the y one, one's positive and one's negative. And so to figure out which one it's supposed to be, I'm going to go ahead and put this into reciprocal form. That's where you take the 5x divided by the x and the -3. So you're like distributing the divide by x. So 5x divided by x minus 3 divided by x. So this can be simplified. 5x divided by x is just 5. And then minus 3 divided by x. Okay, so I can tell this does have a vertical asymptote at x equals 0 because of the x by itself in the denominator. And it has a horizontal asymptote at y equals 5. So let's see if I can write it right here. So for 5 minus 3 over x has a vertical asymptote at x equals 0 because there's just an x in the denominator, so nothing to solve. And then the horizontal asymptote is always the constant, and the constant here is 5. It's not -5. The minus goes with the next term. This is a positive 5, so y equals 5. So that means it is the graph on the left. This one. All right. For rational equations, I'm just going to go over problem A. Problem B and C are really good problems. They're a little bit more than you need to be able to do on the final. And so I'm going to go ahead and just make sure you can do A. All right. So two things when you're solving rational equations. First of all, you have to solve it, and then also state the restrictions, because sometimes your solution is also a restriction, and when that happens, there isn't going to be a solution, or you have two possible solutions, but only one of them actually works because the other is a restriction. So you do have to know the restrictions to be able to state the final solution. So restrictions come from having a denominator of a fraction, so the bottom, a denominator equal to 0. So we've got denominators of x plus 2 and x minus 1, and we just focus on the denominators. So x plus 2 can't equal 0, which means x will not equal -2. So -2 is a restriction. And over here, same idea, x minus 1 can't equal 0, so add the 1. X can't equal 1. So there's the restrictions on the denominator. And now we get to solve. So for solving, you kind of have two options. I'm going to go with the quickest one now that we're like reviewing and we've done this a whole bunch. The quickest way to do an equation like this is to look at it like a proportion, and in a proportion the cross products end up being equal. And we can prove why that works, but for the purpose of solving these equations to review for the final, I'm just going to get straight to solving. So that means that 1 times x minus 1, always put expressions in parentheses, equal to 2 times x plus 2. Again, the x plus 2 needs to go in parentheses. Okay? And so we always want to clean up each side of the equation before we start trying to do any sort of solving. So we have to do 1 times x and 1 times -1. It's pretty simple. It's just x minus 1. And then 2 times x plus 2 times 2. 2x plus 4. And so from here, I might just, you guys seem to like using those railroad tracks. And I'm doing that because I'm just going to move the x's to one side and then the equations or the constants to the other. So basically you're moving like terms so that they're each on their own side of the equal sign. So minus the x, I get negative 1. 2x minus x is x. And then I'm going to move the 4 over. And negative 1 minus 4 is negative 5. And x there. Okay. So my first step, I move that over. Second step, move that over. And I don't need to divide this time because that's just x. So x equals negative 5 is the final solution. And it's a-okay because it's not either of these two restrictions. All right. So I'm going to skip over this row of problems and just look at the next one. So these were like review of Algebra 1 exponent, things you should have learned in Algebra 1 as far as exponent rules go. And then these were new for Algebra 2. And so we're going to focus on that since this is the Algebra 2 final. So write the expression in radical form. And so remember, we had like this rule in the table of exponent rules. It looks like this: a to the m divided by n is equal to the nth root of a to the m. Okay, so the denominator of the fraction tells us what type of root it is. So when we simplify on number 12, it's a cubed root. And then our base stays the same. So our base is 5, and then the top, the numerator of the fraction, is our exponent. So 5 to the 4th. Okay. And then we have some negative exponents. This is like a negative exponent and a fraction. So the fact that there's a negative exponent here, I'm going to address that first. So you have an exponent rule that says a to the negative m is equal to 1 over a to the m. Okay, and we worked a lot earlier this semester on why that happens. And so I'm going to start by just making this into a fraction. 1 over 10 to the 5/4. So I just made the 5/4 positive by creating the fraction. And then just do the work like with the root. So this is 1 over the 4th root of 10 to the 5th. And that's the final answer there. And then number 14 is just like the opposite of number 12. So we're starting here and we're going backwards. So 12 is our base. And our exponent is 2/3. Okay, again, this is the numerator of the fraction exponent, and then the type of root is the denominator of the fraction exponent. Okay. Number 15 and number 16, they're really similar. I'm just going to go ahead and do them both. And let me see here. I need a highlighter because I just wanted to highlight our strategy for solving root equations was to isolate the root and then use an exponent to get rid of it. Isolate it, use an exponent to get rid of it. So we isolate the root there on number 15 by subtracting the 10 from both sides. And that gives us the cubed root of x minus 2. 15 minus 10 is 5. Okay, so I got rid of the plus 10 by subtracting it, subtract it from both sides. And so now that I've got the root by itself, I use an exponent to get rid of it. Okay, and I know the exponent by looking at what kind of a root is it. This is a cubed root, so we use an exponent of 3. So these two, the root and the exponent, they undo each other. So this is x minus 2. And then 5 to the third means 5 times 5 times 5, which is 125. You add the 2, so x is 127. Okay, I didn't worry about whether or not there would be a solution because cubed root equations always have one solution, one real solution. Square root equations have one real solution or no real solution. So let's see what this one has. So for this equation, to isolate this radical, I'm going to add the 3 because it's being subtracted. Notice I am not going to do anything with the 1 because it is under the root and cannot be touched. And then 6 plus 3 is 9. Okay, so we isolate the radical and then we use an exponent to get rid of it. This is a square root, so the exponent we use is 2. So the square root of 2x plus 1 squared is exactly 2x plus 1. And 9 squared, 9 times 9 is 81. From here, you subtract the 1, so 2x equals 80, and then you divide by 2, so x equals 40. Okay, now, had I gotten to this point and my 9 was negative, I could have stopped there and said no solution because this is a positive value. So knowing that this means the positive root, as long as this is a positive value, then you're going to be able to find one solution. If this is a positive root and this is a negative value, then there's no solution because positive and negative numbers don't equal each other. Yeah, so that's it on solving root equations or radical equations. I'm just going to do quickly 2 problems from 18 and then 1 problem from 19. Okay. So we did do 18 in class, but in case you missed it, I'll give it a shot again. And so, all right. And so again, I'm just going to do the P plus Q, and actually maybe I'll just do all 3 of them. Okay, so P is 3 minus 13i, and we're adding that to negative 11 plus 22i. In part B, we're doing the same, except we're subtracting. And then in C, it's multiplication. So we'll get to that in a minute. Okay, so let's start with A, adding. When you are adding, you are simply combining the real numbers as they are. So 3 plus negative 11 is negative 8. And then negative 13i plus 22i, negative 13. Again, if you like just have a hard time doing this in your head, just use the calculator. It's okay. Negative 13 plus 22 is positive 9. So since it's positive, I'm going to write plus 9i. So we have, that's our final answer. I can't combine them. This is real. This is imaginary. They just come together to make a value, but that's how you write it. Okay, next, we have to change this equation because of the minus in the middle. So the minus in the middle makes what comes after it, everything in the parentheses after it has to change, okay? So the 3 plus 13i, or 3 minus 13i, that stays the same. But now minus negative 11 makes it a plus 11. And minus a positive 22i is just minus 22i. Notice I only have one symbol between terms. If you are using two symbols between terms, it makes it so confusing. Don't do it. Do not do it, okay? So now we do the same thing. We combine the real numbers. 3 plus 11 is 14. And the imaginary numbers, negative 13i and negative 22i. So that is a total of negative 35i. So since it's negative, minus 35i. Okay? So adding versus subtracting. Adding, we just worked with everything as is. Subtracting, rewrite it real quickly with new signs. The scribbling signs out and changing them above, not only does it confuse me when I'm grading it, it confuses you because people often get the answer wrong if they're trying to just scribble out signs because they don't want to write too much. This like literally took 10 seconds, so do it. Okay, last one in this section is P times Q. And so let's do that. Please use the box. 3 minus 13i, I'm going to put that on the left side of the box. So 3 and negative 13i. And then we're multiplying by negative 11 plus 22i. So I'm just going to have the 22i be positive. And then we're multiplying negative 11 times 3, negative 33. Negative 11 times negative 13i is 143i, and it's positive. Okay, now the next one, 22i times 3 is 66i. And then 22i times negative 13i, I don't remember what it is, so I'll just do it here. I'm just going to do 22 times negative 13. Negative 286. So negative 286, but I squared. And remember at the very beginning of this unit, we learned that I squared is equal to negative 1. So this is really negative 286 times negative 1. So it's positive 286. And so when you get all of the multiplying done and then you're ready to combine like terms, you're going to combine this 286 with the negative 33. We're no longer going to be concerned with that because it's now a real value. So 286 plus negative 33 is 253. Right? Yeah. So these total to 253. And then 66i and 143i, just I'm really tired, so I'm just using my calculator to make sure I don't make mistakes. It's 209. So plus 209i. Okay, so that is our complex value. We have the real part coming first and the imaginary part coming second. And so we have satisfied the directions for all of these because this just means have the real part come first and the imaginary part come after it. Okay. All right. I'm going to just do, I think, problem A on number 19, just to quickly review. Let's see here. Can I factor that one? 32. Oh, it kind of like it looks like I could factor, but I don't think we actually can. I'll show you why. So I need this to be -8. And so actually, it doesn't even look like we can factor. I don't know what I was thinking there. So I know 8 is, or 32 is like 1 times 32, 2 times 16, 4 times 8, and that's it. And none of them would allow me to add up to -8. So I'm not going to factor. I'm going to use the quadratic formula. Okay. So in using the quadratic formula, I kind of like tried to simplify it for you. Instead of doing the entire formula at one time, I said, calculate b squared minus 4ac first. Okay. So our b is -8. Remember, we absolutely need those parentheses. So -8 squared minus 4 times a, which is 1, times c, which is 32. Okay, and when I put it in the calculator, I'm going to put it in there just how you see it. So that -8 has to be in parentheses, then squared, minus 4 times 1 times 32. I probably didn't need to put the times 1 in there. We get -64. Okay, so this is -64. And in my classroom, there's like a little thing on the wall, and I said, put a box around it. You're going to put that into the rest of the formula. So x equals -8 plus or minus the square root of -64. Remember, that's what goes there, over 2 times 1, 2a. And now we just clean it up. -8 is 8. The square root of -64 is an imaginary number, and 64 is a perfect square. If you're not sure, you can always check a value on your calculator, but use the positive one. Because if you use the negative one, it's going to tell you error, non-real answer. Well, that's because you put a negative number under the square root. So don't check that. Check the positive one like I did here. The square root of 64 is 8. So the square root of -64 is 8i. And this is all being divided by 2. Okay. So I can't like find an answer here and divide. So that's when we split apart the fraction. Okay. So this is equal to 8 divided by 2, which is 4, plus or minus 8i divided by 2, which is 4i. And that is the final answer. And the last problem I'm going to go over in the video. So I know in class I told you I was going to make a video for each section, and then I got a little more realistic about how much time that would take and just made videos over a selection of problems from each section. So this should be great to help you. I would use what's in here to kind of put your note card together. And then any other problems that you're dying to know how to do, if you are stuck, you can ask me about it on Monday. All right. Cheers.